recording. Am I audible and you can see my slide? Can you just write in chat box that yes, you are seeing my slide and I'm audible? Thank you. Okay, so let me start. So, very good evening all and welcome to the problem solving session of the course Analytical Chemistry, which is taken by Professor Devasis Ray. And I am Satya Prakash Yadav, a PMRF scholar. I am working with Professor Satish Patil at Solid State and Structural Chemistry Unit, Indian Institute of Science, Bangalore. So about the course, so this is 12-week course. So in week we have solved the question related to chemical and material analysis method. In week 2 we have solved the question related to role of analytical chemistry and techniques. In week 3 we have basically seen the problem on chemical equilibria and the basis of chemical analysis. And from week 4 to week 6 we have solved the problem based on the spectroscopic method like IR, fluorescence, UV and all. In week 7 and 8 we have solved the problem based on thermal methods like TG, DT, DAC and what are their application. And we have came to week 9. I have already discussed the basic of electrochemistry and the problem related to that. In this week, we are going to some potentiometric technique. So I will explain. So what are the things you have learned in the class wise in this week? So in week 10 lecture number 46, so you have basically learned about the potentiometer cells, how their potential be determined, and you have extensively learn about the reference electrode. Professor has already told about reference electrode and indicator electrode. In indicator electrode he has told you about the metallic electrode, membrane electrode and ion selective electrode. So in which he has demonstrated about glass membrane electrode, and he has told the property of those things, and he also little bit discussed about the cation ion selective glass membrane electrode like sodium, potassium, ammonium, cesium, rubidium, lithium, and silver cation. If you have, what are the ion selective membrane electrode are present? He has discussed about that, and then he went to the potential metric titration in which he has talked about the neutralization reaction, precipitation reaction, complex formation reaction, and redox reaction, and how the potentiometric titration curve look like, from where it will start, what is the first derivative of the plot of the potentiometric titration, what is the second derivative of the potentiometric titration, how it looks like. In assignment it will come and I will tell you. In lecture number 47, basically he has talked about the different types of oxidizing and reducing agent. So he has also discussed about the redox titration curve. So he has taken iron 2 plus and cerium 4 plus titration. Then he has also discussed about the uranium 4 plus and cerium titration. And he has discussed about many titrant solution like iron 2 plus, cerium 4 plus, sodium thiosulfate, IO4 minus, iodate minus, periodate solution, S2O4 2 minus, sodium bismuth oxide. So many oxidizing and reducing agent he has taught in this lecture, and also he has discussed about the redox indicator about the ferrine and ferroin. And then in lecture number 48, he has discussed about the IR drops in the electrochemical cells. What is the origin of IR drop in the electrochemical cell? So one question is also there on the IR drop. So there I will discuss what is the reason behind the IR drop and why it arises, why the cell potential whatever we are measuring is not equal to the theoretical cell voltage. In lecture number 49, he has discussed about the gravimetric methods and its application. If you are going to deposit the metal, so how you can selectively deposit one metal while keeping other inactive. So here I have one slide. I will show you how what are the from the lecture only. So how you can selectively deposit only one metal. Other should not interfere like that, and then control potentiocoulometry and its use. So I will told you about the control potential experiment and coulometry. So these are based, that coulometry is based on the Faraday first law. Basically, how much charge you are giving, that charge will be equivalent to the how much mass it will be deposited. Like 1 Faraday is nothing but 1 Faraday means if you are giving this 96,500 coulombs, 1 mole of the active species deposit. So like that. So now I will come to the um, problems. So first question is, what are the criteria of the secondary reference electrode? So it's showing that it should be chemically reversible. Thermodynamic coefficient of potential should be small. The potential remain almost constant when small current passes, and all of them. So now I will ask to write the answer for this question number 1. Then I will explain what are the criteria for the secondary reference electrode. So I will also tell about what are the primary reference electrode and secondary reference electrode. Can anyone just write in the chat box that can anyone write in the chat box what is the answer for question number 1? If you don't know, you can just write. Okay. Sweta is saying A. Okay, Sunil, you have any other opinion? Any other opinion? Okay, so the answer is D. So I will come why that answer D is correct for this. So first of all, what is the primary reference electrode? Primary reference electrode. So you have here platinum wire, and you are bubbling the S2, and you have taken the 1 molar HCl solution. So here you are bubbling the. So this hydrogen electrode is your primary reference electrode. So here the activity of H plus ion is 1, and this hydrogen pressure is 1 atm. So this potential, this E H2 by H plus is 0 volt. This is the convention, right? So this is your primary reference electrode. But to to this is the platinum wire. So I am already so so this is the primary. But the challenge with the primary reference electrode is that to control the pressure at 1 atm and activity of SCl should be 1 and the platinum. This is the costly setup and it is not you whenever you require you have to make it this primary reference electrode. So people has come with the secondary reference electrode. So in the secondary reference electrode, what are all the example? Your AgAgCl reference electrode, standard calomel electrode, mercury mercurous sulfate electrode, mercury mercurous oxide electrode. So these are your secondary reference electrode. And what are their criteria? So the first criteria that it should be uh, electrochemically. First criteria, they should be electrochemically reversible and chemically also. Okay, so first option is correct. Second option, that is their thermal coefficient d by dt. Thermal coefficient should be small. So your d by dt is nothing but your entropy. So delta S is equal to nothing but minus nf d by dt. Right. So d by dt is related to your entropy. So there should be minimum entropy change. And the third and the most important thing that their potential should be constant when small current passes. So whenever we are passing the small current, their potential should not change. This is the criteria of non-polarizable electrode. Okay, so what is like suppose you have this I and this is your E. So whenever we are passing the small current, so it should be like this. Their potential should not vary much like this something. Okay, so this is the one important criteria and this drift should be minimum. One more important, d by dt should be minimum. Like your reference electrode potential should not change over the time. That is the one other important criteria for the reference electrode. So it is reference electrode because its potential is fixed. It is not changing over time. So that we can characterize other electrode with this reference electrode. So got it? Like what is the primary reference electrode? Why we need the secondary reference electrode? What is the criteria for this? This the secondary reference electrode. So Sweta, I think now you have an idea about the reference electrode, primary reference electrode, why secondary reference electrode came into the picture, and what are their criteria. Okay, thank you. Now coming to the next uh, 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 is, uh, question. What is the correct statement of the glass electrode? It is a ion selective electrode. It is commonly used for pH measurement. Glass electrode are sensitive to the single charge and all of these. Now can anyone answer for this glass electrode? Yeah, Sunil Pawar is saying that D. Any other opinion on this question? Let me check that recording is going. Yeah. Okay. So now I will just start um, tell you what is the answer for what is the correct statement for the glass electrode. So basically the answer D is correct. So what are the glass electrode? So glass electrode is a kind of your ion selective electrode which is made of doped glass membrane. So it is made up of doped glass membrane. Okay, so and these are sensitive to the single charge ion like proton or silver ion, and there are so many other glass membrane electrode which will be sensitive to the your ammonium ion and this other like cesium ion, rubidium ion. These are the sensitive to a single charge ion, and they are commonly used in your pH measurement. That is also correct, and their voltage is basically related to some reference value which is sensitive to a change in the activity of the certain type of ion which is your a singly charged uh, cation like singly charged cation like proton, silver, ammonia. Okay, so I think Sunil Pawar is correct. The answer is D. Which anion is detected by the sodium thiosulfate as a titrant? So periodate, chloride, sulfate, and none of these. So this question is basically coming from the lecture number 47, where he has discussed about this different types of oxidizing and reducing agent. Sunil Pawar is saying A. Okay. Any other opinion? Like Shweta, you can also write like what you think that what should be the answer for this question number 3. Sunil, can you give me some hint? Like what kind of titration it called? Redox titration, but it has some specific name also. It is redox titration. It has some name also. Okay. So let me go a little bit in detail. Yeah, correct. Iodometric titration. Sure. So I will just go little bit in detail. So how you are going to? So basically, this is iodometric titration. So we know that like if you have this IO4 minus in acidic solution, it will give you the half I2 plus 4 water. So basically, this is iodine can be titrated with your sodium thiosulfate. So if I ask you, can you find out this uh, iodate with this sodium thiosulfate? The answer is yes. If you have this 5I minus in acidic solution, you will have this 3I2 plus 2 water molecule. Now again, I2 will I2 can titrate it with sodium thiosulfate. Now, if I write the reaction for sodium thiosulfate with iodine, so what will form? It will form the this I minus 2I minus plus S4O6 2 minus. So if I balance it, here you write 2, here you write 2 sodium iodide in this paper. Now, what are the important criteria for the iodometric titration? So there is difference between iodometric titration and iodimetric titration. So your iodometric titration, in that you are using directly the iodine. You are directly titrating iodine with the uh, your titrate. But here what we are doing, we are generating the iodide ion, and then we are going to uh, titrate with sodium thiosulfate. So sodium thiosulfate is going to form this sodium tetracyanate. Thionate. Okay, this big file. Now, so once you are doing this iodometric titration, you have to keep something in mind. So first thing is that, like, if I talk about this thing, so you have to put the excess of Ki. Why? Because your iodine is volatile. So basically, you will form a stable complex which is Ki3, like basically I3 minus. And now this will, this is a like weak complex which will act as a source of iodine. This is the first thing. So iodine is very like volatile. So you should not shake the uh, vigorously, because iodine will uh, evaporate if you shake the vigorously while doing the titration. Second point is that iodine also a indicator indicator, but to get the more accurate endpoint, we use the starch indicator. So starch will form a, like it will form a complex with iodine, and it will give a blue color complex. Now, one more important thing, that starch should be freshly prepared, and other thing that it should put before the endpoint, not initially, because if in initially the iodine concentration is very high and it can form a stable complex with starch, which will not go at the endpoint also. So which will leads to a wrong endpoint. That is the and other important things we have to keep in mind. Okay, so these are the things we have to keep it in mind. Okay, so that's it. And another important thing, that you have to maintain the pH of this solution. So we have to use cold water. Why? I don't think so, because I have performed this iodometric titration to find out the concentration of iron and this cuprous iodide. We haven't used the cold water solution. At least I haven't come across to use this cold water for this thing. So the only thing is that we take the this your solution, which we are going to which concentration we are going to find out, like we have to use cold water for iodine. uh, I haven't come across for like this. So what basically we do, we take the suppose if I am going to find out this cuprous iodide iron 3 plus complex. So iron 3 plus we have in that solution, like FeCl Cl3, we put Ki in excess, and we put the watch glass and kept in the dark, because under sunlight also the reaction can accelerate. So we have to be then watch glass be with watch glass we kept it inside the like a drawer in dark, and then we take out the solution and try to start the titration. And before the input we have to put the start solution, like that. But I haven't come across like we have to use the cold water for iodine. I will check and let you know in the next class if there is such thing like we have to use cold water for iodine. Okay. So these are the things we have to keep in mind while performing this iodometric titration. Now this one, question number 4, this AgCl Cl minus cadmium 2 plus cadmium. What is the reference electrode used in the above cell? Silver chloride, cadmium electrode, hydrogen electrode, or platinum electrode? Can anyone write in the chat box that what is the answer for this question number 4? Answer number C. Okay. Anyone else? Like what is the answer for this question number 4? Shweta, you have any other opinion for this question number 4? Yeah. So the correct answer is A, because in this uh, cell we have two electrodes. So left hand side we have silver silver chloride Cl minus. In the right hand side we have Cd2 plus Cd. Now we have already discussed about the secondary reference type electrode. So your silver chloride in Cl minus, basically we use the KCl. So here your potential will depend on the concentration of KCl used. So if you have used the saturated KCl, you can use 3.5 molar KCl, you can use 1 molar KCl, you can use 0.5 molar KCl. Then potential will accordingly change, because your E is nothing but E0 minus RT by NF, which is RT by F, because N is the number of electron transfer, which is 1, log ln concentration of activity of Cl minus. So your the concentration of Cl minus is the one which determine the this reference electrode potential. So basically we used to use the mostly the saturated solution in KCl. So here your silver chloride is the reference electrode used in this cell. So in the right hand side, basically your cadmium is reduced to the cadmium is reduced to the cadmium 2 plus is reduced to the cadmium metal. So your reference electrode is the um, silver electrode, because this potential will depend on your concentration of you have LNCD2 plus concentration. Now once you are charging the small current, this concentration will fluctuate. Accordingly you will see the change in the potential. But in this, what is happening, your silver chloride and Cl minus you have. So this silver, how we make this reference electrode? Basically we take the silver wire and we will use the potentiometric experiment to deposit the very thin layer of like 50 micrometer or 50 micrometer of silver chloride. Now, and what we do, we basically then put in the solution of this KCl, which is saturated KCl. Now, this potential will not change because your Cl minus is the concentration will fix. Here, very small change will happen, right? So this is your reference electrode, which potential is fixed, and you can change the, you can take the contact from here. from this silver wire. So you can join silver with platinum, or you can take out silver itself. But silver, if you keep in the moisture, it will form oxide layer. So you have to be very careful while taking out the this connection. So that's it. So Surya, is it clear why this silver? Because if any cell reaction is written, you have to find answer within these two. Because in hydrogen electrode reaction, here it is not required. Either platinum electrode also is not written. So it will be either AgAgCl or cadmium to cadmium. But this metal kind of electrode, their potential is highly dependent on the cadmium 2 plus. So it will not be used as a reference. So what do you mean by IR drop? It is a potential difference, it is a current difference, it is resistance difference, or it is the concentration difference. So can anyone tell the answer of question number 5? Yeah, Sunil is saying it is a potential difference. Yeah, Sweta is also saying. So yeah, so the answer is yes, it is a potential difference. Now the question come, why there is a IR drop? So let me tell you, let me make a simple cell, okay, which has two electron. Okay. Now you wanted to measure the voltage difference between these two cells. So this can be anything. Suppose you can take copper 2 plus and zinc 2 plus. You can take a simple reaction. Now, why there is a potential difference? The potential difference arises. So let me write. So suppose this side, this zinc is going to the zinc 2 plus. Now it has two electron transfer. This side, what is happening? Your copper 2 plus taking out two electron, and it is going to, sorry, copper 2 plus is a, yeah, it is depositing copper. Now what happens? Two electron transfer is coming from here to here. Now, so suppose here we have this zinc, right? Zinc is went to the zinc 2 plus, and here that copper 2 plus went to the copper. Now this, suppose you have taken the copper sulfate. Now copper sulfate, so this is 2 minus copper 2 plus, this sulfate minus iron, here it is alone, and here that zinc 2 plus ion is there. Now this sulfate ion should go near to the zinc, so that it should be the charge neutral condition, should charge neutrality should be maintained in this reaction. But there is a solution in between these two electrodes. Now this solution is basically a resistance, because to migrate a ion from one place to another place, it will be hindered by the molecule present in the solution. So those hindrance is nothing but a resistance. That resistance which is like stopping to move this sulfate ion to the near the zinc electrode. So this is called the solution resistance, RS. Right. So now if your voltage, if you are going to measure, so which is V cell minus IRS. This will be the V measured. Right. So this is the voltage difference. Voltage difference is V measured minus V cell is nothing but your IRS. Okay. So the question is now other question. Other question, like how we can minimize this IR drop. So this can be minimized by introducing a new electrode. So basically we go from the two electrode system to the three electrode system. So if someone asks why you need the 3 electrode in the cyclic voltammetry experiment? Maybe it can come in the next week. um, Next week lecture you might get to know about the cyclic voltammetry. So if someone asks why you are going from 2 electrode to 3 electrode, so you can say that suppose you have one electrode here, another electrode here. This is the solution resistance RS is here. So corresponding the voltage drop will be the IRS. Now what we are doing, we are keeping one reference electrode closer to the your working electrode. Now your resistance will drop here. Now this is called RU. So RU is nothing but uncompensated resistance. Uncompensated resistance. Okay. So what we are doing, we are measuring the potential with respect to reference electrode, and we are measuring the current between the working electrode and counter electrode. Now the question is, can we remove this uncompensated resistance? Answer is no, because in ideally the working electrode and counter reference electrode should be at same place, but we can't keep it at same place because there will be the electric field disturbance between this working electrode and reference electrode. The question is, okay, how far this working electrode and reference electrode can be kept? So if reference electrode tip diameter is D, so we can go minimum 2D distance. So across the 2D distance, what is the resistance which is RU, which is called the uncompensated resistance. Got it? So why we are going from 2 electrode to 3 electrode? What is the uncompensated resistance? What is the solution resistance? And why we are seeing the voltage difference? I think this will have a clear-cut idea about the IR drop. And one more thing professor has told in the lecture, so I can tell you why. So your potential, suppose you are measuring with the current, so it will be like this. So I am showing you a battery data. So how it will look? It should go first small drop. Sorry, this will be a small drop, then will be a linear, and then it will go down with I. So the question is, what is this first drop, what is this linear drop, and what is this final drop? So the first drop is come by the activation potential. Activation potential, it is fixed with the current density. So you have some small activation over potential with the I. So after that activation potential, your IR drop will come. This is called IR drop region. So once you increase the current across the resistance, whatever you have the solution, because you are increasing the current, so you will get the more IR drop as we increase the current. Now the third drop, this is called the mass transfer polarization. Mass transfer polarization, or you can say that concentration polarization. So what is happening here, once you are giving a very high current, that electrode is not get enough supply of the your redox active species towards the electrode, so it will further see the difference in the potential, so it will immediately go down that difference. So these are the three kinds of over potential, or you are saying that drop in the potential in the your battery and all. Okay, so now I will go to the second. What is the principle of the electroplating methods? Can anyone answer now the question number 6? Okay, Sweta is saying that. Okay, so yeah, you are right. The deposition of one metal over over the another metal is nothing but your electroplating. But the answer is D, because it is the based on the this theory of the hydrolysis. So what happens when we do the like electroplating method is nothing but a deposition of one metal over in another metal in presence of metal salt. which is the in aqueous solution. But water molecule is released as the final product in this process. So as a consequence, your electroplating is based on the theory of hydrolysis. Okay, I think now you have got the answer why it is the answer number. Because finally you will see a water molecule is releasing as the final product. So this is called the uh, theory of hydrolysis. It's based on hydrolysis. Right. Can I go to the next question? Because next question is even more important. Can you write in chat box that I can go to the next question? Yeah. Okay. What happens when the electrodeposition of copper tin mixture occur in presence of tartrate ion in a cathode with platinum? Both copper and Sn are deposited. Only copper is deposited. Only tin is deposited. Any of them cannot be deposited. Now, can anyone tell me that what is the answer for this? Because if you have went through the lecture number 49, I think most probably there you have seen the like which one will deposit on this like if you have the presence of tartrate and why only that metal is deposit, other will not deposit. Can anyone write in the chat box? What is the answer? Any guesses? Like whether both will be deposit or only one will deposit? If one is deposit, which will deposit, or any of them cannot be deposit? Any guesses? Sunil or Shweta? Yeah, Shweta is saying B. Why B? Why not C or A? Okay, so let me explain. Okay, Sweta is right. So why only copper will deposit? So what people usually do, suppose you have the uh, two or more than two metal ion. So what we do, like if both the metal are free, right? So both will deposit if potential are nearby, because you have to give the excess over potential because of I told you that IR drop and activation over potential. So if both are like both your copper and Sn both are in +2 state, right? But what is happening when you are using the tartrate ion? This tin is there which is forming a complex with the tartrate ion. Tartrate. Now, once you have a free metal, once you have the metal with bounded like under the complex, those both will behave differently. So this will remain as a solution. Now only your copper 2 plus will deposit as a copper. So either it will be SN2 or SN4. Both will form a complex with the tartrate ion. So basically your tartrate is the anion. So it will form an anionic binding species with the tin, and it will remain as a in the solution, and copper will be free. It will be deposited. So I will show you that what are the different kind of this anion people have used like electrolyte to deposit selectively. So if you want to deposit silver, you use the acetic or acetate buffer. So any other which will not be, which can be present and it will not affect copper or any heavy metal. If you have copper, so you use the tartrate hydrogen and Cl minus. So if whether you have bismuth, antimony, lead, tin, nickel, cadmium, zinc, it will not be interfere. So similarly, if you want to deposit the bismuth, so you have to use the tartrate and hydrogen and Cl minus. Now see, copper if there, then copper will deposit. But for bismuth, the other ion can be present like lead, zinc, antimony, cadmium, tin. So these potential are versus a standard calomel electrode. So keep in mind, if you are changing the reference electrode, this potential will change. Suppose you have this antimony. So if you have antimony, you use this HCl hydrogen at 70 degree. Other metal, lead and tin can be there. So you have to like first you identify what are the element is there. Now you have to go. You have to choose which ion you are going to deposit. Then based on that you use the electrolyte and deposit that metal selectively. That is the important thing here. Okay, I think Sunil. So did you get it? Like how, like what is the application of the control potential um, technique electrolysis? So which metal you are going to deposit? You have to identify what are the other element, how you can mask other element and deposit selectively the choice of the metal you are going to deposit. So these are the different uh, 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 electrolyte people have already reported in the literature. Okay, so other okay, let me go to the yeah. So only copper will deposit. Now question, which indicator is used for the determination of cerium in titration of cerium 4 sulfate with sodium oxalate? Now this again come back to the lecture number 46. So I have already told like what is the redox indicator. And this indicator I have already told in one of the previous lecture also. Once I think somewhere it is this you are going to determine the iron 2 plus. So I already told you like what is the complex farming that iron 2 plus. Think some of the lecture I have told you already. And that time I told that this is a very important redox indicator also. Can any one of you now tell me, Sweta is saying C. Methyl orange, no. Sunil, can you guess what is the answer for this question number 8? Yeah, you are right. The ferroin indicator is like suitable indicator for this thing. So first of all, I will write the what is the equation. So you have cerium 4 plus. Once you have sodium oxalate, okay. So this will go to the cerium 3 plus, 2Na plus, and 2CO2 will. So this is a redox reaction where your cerium 4 plus is going to cerium 3 plus and sodium oxalate is going to the CO2 with 2 electron. So basically 2 electron here it is releasing, it is taken by this. Now what is the role of the ferroin indicator? So you have you are titrating cerium 4 sulfate with sodium oxalate. So once cerium will get over, basically it will oxidize or reduce your ferroin. So what is ferroin? So it is the 110 orthophenethylene complex of iron. So I will just write what is the 110 phenolphthalein. So you have benzene ring, then you have this nitrogen group here. Okay. You have this a bidentate ligand. So this will format iron. So you have other also. So you have like three. Okay. So you have one, you have two, you have three. So basically it is FeO phenon 3 phen thrice. Now if it is in 2 plus, it will be in red color. If it is in 3 plus O phen, this will be as a blue color complex, right? So this is called ferroin and this is called ferrin. Okay, so you can detect by the changing color from red to blue. So cerium 4 plus, if you are doing the titration with sodium oxalate, you add a pinch of ferroin and ultimately you will see the color. So Sweta, is it clear how why we are using the ferroin? And one more thing, professor has already told you about, if you are substituting at 5, here you are putting the R group. So you can tune the potential of the oxidation. Okay. So how I think I have written somewhere. So where is that? Just give me a second. I will tell you. Where is that? Oops. Yeah. So if you suppose you have R is NO2, right? And so first of all, this has, if R is H, it will be 1.11 volt. If your R is NO2, it will be potential is 1.25. And if R is CH3, sorry, if R is CH3, so its potential is 1.02. Because here, the main idea is once you substitute the your electron withdrawing group and electron donating group, so you can change the your redox potential. So basically, electron withdrawing group will stabilize the LUMO, because then ultimately you will go to the more positive potential, and electron donating group will stabilize your HOMO, so ultimately you will go to the lower voltage. So this is your concept here. So this is commonly used in non-aqueous redox flow battery, which I am working. What is the role of this electron withdrawing group and electron donating group? Okay, so this can be said here. So your electron withdrawing group affect the LUMO and electron donating group will affect the HOMO. So once you are changing the HOMO and LUMO, accordingly your redox potential will change. Because in the previous lecture I have told you like how HOMO, LUMO and Fermi level of this electrode depend what is the oxidation and reduction. Okay. So question number 9. Choose the incorrect statement for the potentiometric titration. Can anyone? This is again the again from the lecture number 45. Can anyone write in the chat box? What is the answer? Choose the incorrect statement for the potentiometric titration. It is similar to the direct titration of redox reaction. Here indicator is used. In this method, potential is measured. Measured is with the addition of the titrate. Sunil Pawar is saying B. Sweta, you have any other opinion? Or you are also going with answer number B? Any other opinion? Or okay, I will just go ahead and explain. So first of all, what is the potentiometric titration? So in this potentiometric titration, we measure the cell potential with respect to like here versus some reference electrode, like suppose your standard calomel electrode. Okay, yeah, you are right. That is the answer is B. Okay, versus the addition of the or volume of the titrate, volume of the titrate. So in y-axis it will be the cell potential. In x-axis it will be the volume of the titrate. Now the graph will look like this. So it will initially first it will be the potential of the species present at the initial, where basically your which species you are going to determine. At the end point, both the species concerned redox potential will be balanced, your titrate and your analyte. After that, the potential will be the coming from your titrate only. Now, end point is basically determined from this SAR, this potential change uh, against the volume of the titrate. So this potential, so you have to find out where the end point is. So you take the first derivative. So once you do the first derivative with volume of titrate, basically how it will look like, it will go like this. So this is your end point. If you taken the second derivative, how it will look like? It will go like this. So this is your end point. Okay. So in the initial, I had told you like in one question, I will tell you what is the first derivative and second derivative in the first. So here we are not going to use any indicator. What is the indicator for this in point calculation is the this sharp change near the sharp change in the potential near the end point, which is the main reason to determine your end point. Okay, so both were right. Like the incorrect option is here indicator is used, and it is similar to the redox titration because you are using one side the iron. Suppose you have taken this iron 2 plus iron 3 plus, on the other side you have taken cerium 3 plus cerium 4 plus. So this is the redox reaction one, and we are measuring the potential of this redox species. In initial, it will be the iron 2 plus, iron 3 plus. At the end, it will be the cerium 3 plus, cerium 4 plus. Okay, here the both the potential will be more or less same. Okay, so next, the final question is, which one is used as the oxidizing agent in the redox titration of the uranium 4 plus? Can anyone just write? Because in the lecture number 47, professor has nicely told you about this um, uranium 4 plus titration and iron 2 plus titration, and he has also given the voltage range that 0.3 to 1.5, how he has make uranium 4 plus is down, Fe2 plus is up, like that. So can you just quickly tell me what is the answer for this question number 10? Anyone? It will be the hydrogen. It may be it is hydrogen peroxide, lithium aluminum hydrogen arsenic ammonium nitrate. Anyone? Sweet, what is saying it? No, this is not the correct option. Sweta is saying B. this is also not the correct answer. Okay, so first of all, this is the reducing agent. Okay, and here we are finding the oxidizing agent. Lithium aluminum hydride is well known reducing agent. This is also a reducing agent. Hydrogen peroxide can act as an oxidizing agent, but this will not suitable for uranium. So the correct option is ceric ammonium nitrate. So what is ceric ammonium nitrate? So cerium, here it is in 4 plus. It will form a hexa nitro complex. So basically you have this 6 minus, here you have 4 plus, so you have 2 minus, which will be balanced by di. So this is ceric ammonium nitrate in the cerium 4 plus oxidation state. Now what is the redox reaction will happen? Uranium 4 plus, here first cerium 4 plus will go to the cerium 3 plus electron, and here uranium 4 plus will take water molecule and it will form a uranium oxide. This is UO2 2 plus 4H plus. Okay, now plus, now you can write 4H plus 2. So here you have the 4 plus, so you can balance it. So it will be here electron 2, so you multiply it by 2 electrons. So this time you have okay, so we have to balance it, right? UO2 plus 4H plus. Okay, so basically you can write uranium 4 plus 448 plus 6 plus 2. Okay, now what we can do, right? Oh, sorry. Yeah, electron will be this side and this will be 2 electron. So you have to multiply it by 2. So first of all, here we are finding out a oxidizing agent, which it should reduce. So say cerium will reduce to cerium 3 plus and it will oxidize your uranium 4 plus to UO2 2 plus. So this is the correct answer, not the hydrogen peroxide, lithium aluminum hydride and hydrogen. Okay, so got it. So cerium 4 plus is the oxidizing agent, so it will reduce your this uranium, this uranium 4 plus. So other thing I will just um, upload to the, like this one, what is called on the web, this one Google Drive has been